All right.
You see those rescue pictures on Instagram? The bio. Okay.
All right. So we last time we talked about what the chain rule was, and we started to do some examples of using the chain rule to do some stuff. I'm going to just kind of continue grinding through some examples here. No, that'd be tough for you to follow along with whatever it is I'm doing if you can't see it. Everybody's okay now?
Yeah, I just feel like we didn't start at the example last class.
We did one, I think.
Oh,
I think we did
it was
one.
very rusty.
Yeah, I know. It was very
quite
rushed.
Something.
Yeah.
Alright, I think I still got that one. I don't know which.
Okay. So the chain rule, again, when we use the chain rules, if we have a composition of two functions, which we have here, right? We have a trig function and a polynomial function composed together. Everybody's cool with that? So the verbiage that I like to use and the way I like to think about this is I like to think about an outer function and an inner function. In this case, the outer function is the sine x, and the inner function would be x squared, since the x squared has been plugged into sine x. Everybody's okay with that? The chain rule says the derivative, or the chain rule of a composition is the derivative of the outer function times the derivative of the inner function. So the derivative of sine is cosine, and whatever was inside just stays the same. And the derivative of the inner function would be 2x. And I'm done. That's the chain rule. So just the derivative of the outer times the derivative of the inner. That's it. It's okay there?
So no simplification. You can't do anything further.
I mean, you could write this as 2x cosine x squared, but like, who cares? Yeah, I mean, like, who cares? You're just rearranging symbols now. Mr. Kulik's not going to mind. And again, as far as like the AP exam goes on the free response sections, when the calculus is done, you don't need to continue simplifying. But if you make a mistake in simplifying and you represent that final answer, even if you did the calculus part right and you screwed up the algebra afterwards, it's still going to be wrong then. Unless it's a show that like the derivative of this is equal to answer, you don't need to simplify.
Okay.
So like do the calculus and you can stop. Okay?
Same with like the other stuff from like 2.2 and like.
To a large extent, yeah. I mean, if it's a multiple choice question where it's like you have to kind of, to be sure you have to end up at one of the answers, that's kind of a different story. Or if it's like a question says show, blah, blah, blah is equal to this thing, then simplifying matters there. But if it's just like, do the derivative of this, you don't have to simplify. Just do the derivative and stop. And I think that's the same standard that I'll take on the on our tests. So let's say we have sine squared of x. What's the outer function? Nope. X squared is the outer function. Remember that sine squared of x really means this, right? Means sine x times sine x. The outer function is the x squared. The inner function is sine. You guys see that now? Little tricky, but like once you've seen the trick, it's like, okay, I can handle that. So the derivative of x squared is 2x. So I'll have 2 sine x. And the derivative of the inner sine x is cosine x. Does anybody recognize this?
Oh my god.
That is a trig identity. That's the double angle for sine. Now, would I expect you to catch that? Nope. But if it was like, show that this derivative is equal to 2 sine x, then I would, that's how you would do it, is you're just using a trig identity there. Okay. So let's look at one of the reasons why the chain rule is so very powerful. So look at this guy. Before the chain rule, what would we have to do? You'd have to do the binomial expansion of that to take the derivative piece by piece, right? Yuck. Here, if we do the chain rule, the derivative of the outside is just going to be 100 whatevers to the 99th. And the derivative of the inside is going to be if you want to write the minus 0, you can. If you don't have to. And again, if you wanted to clean this up a little bit, you could call it 300x squared. But like, Mr. Cool ain't gonna sweat that. Anise.
So how do you know if it's the inner or the outer?
Sure. So what you'd want to do, or what you can do, is I would think about this as like f of x equals x to the 100, and then some g of x equal x cubed minus 1, right? So you would ask yourself, okay, does y equal f of g of x? Or does it equal g of f of x? You know what I mean? Well, this is what we have, because the g of x has been plugged inside of f of x, right? So we can see that the x to the 100th was the outer, and the x cubed minus 1 was the inner. Is that?
Yeah, that makes sense.
Okay. Again, you don't have to ever write out any of this stuff for me. If you don't want to. If it helps you, feel free. And even so, like, remember that the chain rule, the derivative was what it was, or the chain rule itself, we called it, I think we used this notation, where I used cap f. Right, like that was the chain rule. So if you want to think about it symbolically first and say, oh, okay, well, like, here's my g, here's my f, and you do like f prime was 100x to the 99th, and g prime was 3x squared. So if I did like f prime of 3x, of x cubed minus 1, well, that would be 100 x cubed minus 1 to the 99th. And then this was times g prime of x, so this would be times the 3x squared. Right? You can just think about it symbolically too, if that's more convenient for you. And again, when you're starting, it probably will be, right? Like, there's no reason that you wouldn't want to do that as you're starting out. For easy chains, we want to get to the point where it's like kind of a mental math almost problem. But if we get like some of the nasty things we'll look at the end, where they have like several chain or product or quotient rules kind of all rattling around in the same problem, they're doing things symbolically, like it makes it much easier to keep a track of everything. Okay, Sean?
Can you have like 3 functions and composite functions.
Yeah, let's look at an example of that. But before we do that, I want to look at some situations where we can use algebra to make our lives a little bit simpler. So if you look at this problem, what do we have to do? What rules are we going to have to use? Looks like there's going to be a quotient and a chain rule in this, right? Because you'll have to use the chain when you differentiate the cube root of x squared plus x plus 1. Well, what if we think about it this way? What have I accomplished by doing this? Just the chain rule now, right? And comparatively, which one is the which is the easier one to do? The chain rule, right? Like that's enormously helpful. So the outer function is that x to the negative 1/3. Everybody's cool with that? And the inner is the x squared plus x plus 1. That's good enough. If you wanted to be fancy about things, you could write it like as a fraction. But like, who cares, right, Mr. Kulik? The first thing is fine with me. There's a time to be picky about simplifying, and then there's a time to just like get over it. Okay. So let's look at some combination ones now. So we're going to look at some of these problems that are like chain and quotient, chain and product, all three, or multiple chains, like 3 chains in a problem. So we're just going to look at some more complicated examples. Everybody cool? So this is fairly just like computational right now, right? Everybody see that? So we have a quotient rule stuck inside of a chain rule, right? So this might be a situation where it's convenient to think about this as several pieces. So maybe I'll think of f of x as my outer, g of x as my inner, and maybe we'll call this everybody's okay with what I've done there? I shouldn't have picked G here. I'm just going to change this letter to be something else. There. I won't get that far down in the alphabet. I don't want 2 G's rattling around in the same problem, though. That's going to get confusing. All right. So if we do this, we're going to have f prime of g of x times g prime of x. And g prime of x is going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over denominator squared. Everybody's cool with that? So the advantage here is that to write my answer out, all I need now are the derivatives for f, h, and k, which are all easy to do because they're all polynomial. So the derivative for f, for h, and for k. Boy, these are supposed to be t's everywhere, huh, Mr. Kulik? Whatever. You guys can hang with me, right? This is the place where I really made a boo-boo. Down here. Up there, it was still acceptable to make those x's, but down here, those really have to be t's for this notation to make any kind of sense. I'm sorry, guys. All right. So f prime, so 9, and then I got to plug my g of t into the x spot. And then I have k of t plus h prime of t minus h of t. Oops, sorry, h prime of, oh yeah, okay. Yeah, okay, that's all stuff. Okay. And I have h of t times k prime of t. And then Mr. Kulik would like to simplify this piece because that's pretty minimal simplifying and it certainly makes a big difference. So what do we give there? We have 2t plus 1 minus 2t plus 4. If we really wanted to get fancy about this, oops. What could we do? We call this 45 t minus 2 to the 8th over 2t plus 1 to the 10th. But really the step before that would have been fine for Mr. Kulik. Now, what we did there symbolically made life much, much easier than trying to grind through two of those rules at the same time because there's just a lot less symbol copying to have to do, which is a place where errors can get made really easily. It's just we've copied something down wrong or we get like hung up in all the details. And just doing that symbolically with function names first really kind of streamlines that process and simplifies what it is that you actually have to take derivatives of and put back together. Let's see. I don't even remember what letter I'm on. F. Okay. So we have y equals 2x plus 1 to the 5th times x cubed minus x plus 1 to the 4th. What do we see here?
Two new chains.
Yeah, two chains and a product. So I would call these guys like and then maybe we'd say like f of x equals h of k of x, where h of x is x to the 5th and k of x is 2x plus 1. And g of x be like j of L of x, where j of x is x to the 4th, and L of x is x cubed minus x plus 1. So if I were to rewrite this, then I'd have y equals f of x times g of x. So y prime is going to be f of x times g prime of x plus g of x times f prime of x. But g of x is really going to be j prime of L of x times L prime of x. And then f of x is really going to be h prime of k of x times k prime of x. And now all I need to do is just plug in my derivatives, which are easy to get, right? So that's 5x to the 4th, 2, 4x to the 3rd, and then 3x squared minus 1. Everybody's cool with that? Okay, so put a bracket here maybe. So I have 4 something to the 3rd, and then L of x needs to go on the inside, which was x cubed minus x plus 1. And then times L prime of x, which is 3x squared minus 1. Then I have my g of x. Then I have h prime, which is 5 somethings to the 4th. Inside of that was my k of x, 2x plus 1, and then times k prime of x. And then that ought to do her. If you wanted to get sneaky, I guess there's some factoring we could do on this and maybe some decent simplification. All right, let's see, what could we take out if we wanted to, if we were so inclined? Nope. I can take out the biggest power there is to the 3rd, and the biggest power there is to the 4th. And then I guess I could do some foiling or whatever to simplify that more if I wanted to, but like, Mr. Kulik doesn't need you to do that. He would have been fine at the previous step. But again, if this was like a show this kind of problem, that's what I'm trying to do, is pull out some greatest common factors and simplify the stuff that's left. Let's see, did I do that? I did do that when I did this. So eventually you could get down to, I guess the 2 would have been easy to see that you could have taken out, right? And then this stuff turns into 17x cubed plus 6x squared minus 9x plus 3. Well, whatever, right?
So easy to get lost in sauce.
Yeah, but this, like doing this, I think makes life enormously easier. If you're able to do the derivative symbolically, there's way less note keeping to kind of keep track of on something like this, where if you did this with just the symbols in there straight away, you have like 3 layers of copying stuff down, where it's like, wait, have I done the derivative of this or not? You know, like here you can see like, oh, I forgot to write down the derivative of the inside. And because all it is like L prime of x, it's easy to catch that. Versus if you have like a whole line of symbols where it's like, did I do the derivative of the inside there or not? Which one is the inside? You know, like it becomes really tedious to keep track of. Do you want to do one of these like as if I were doing it without doing the symbolically, so you can kind of see how big of a pain it looks like?
If you want to do it.
I would not. I mean, I think that
Can we do another one of these where we use?
we don't do this. We don't do it symbolically. We
No,
just.
where we do it.
That's what we have been doing,
Oh yeah.
right? Like, what we do is we get the symbolic answer, and then we just take the derivatives of the individual pieces and plug them back in. So we're not really like, this is the step where we did all the rules.
Yeah.
After that, we're just using like basic derivative rules to get the pieces to plug back in. There's, like some people would go and try to write that thing in green with the symbols all in it straight from jump without doing it symbolically. And like I can do that. But like the first time you're doing these, you probably can't do that correctly. It's quite difficult. As you get better, you don't have to do things symbolically, but I'd start off doing things symbolically for anything that involves more than one rule. If it's just one thing, like just a product or just a quotient or just a chain, I don't think you need to do it symbolically. But I would do anything that has more than one symbolically first, and then fill in the little pieces afterwards. I think you're much less apt to make a mistake doing it that way than trying to go and do it all at once.
So like the first thing you need to realize when you're looking at a problem like this, is what type of problem.
Yeah.
But then, how do I make this easier to translate that?
Yeah, exactly. So write it symbolically, do the calculus symbolically, and then take the actual function pieces, do those derivatives, and plug things back in. And I think that makes life, oh boy, easier. All right, let's do a couple more. What are we on? F, right? CDF, G is next. Here's one for you, John. So if you look at this, f of x equals sine of, cosine of, tangent of x. I see 2 chain rules nested inside of each other. So I would say that g of x is going to be sine x. H of x would be cosine x. And then k of x would be tangent x. So f prime of x is going to be g prime of h of x, oh, I'm sorry, h of k of x times h prime of k of x which is h of x, or h prime of k of x times k prime of x. Is everybody okay? Now sorting through that symbolically, like, yeah.
Try to cross it.
Yeah, take a minute. So again, we had the derivative of the outside times the derivative of the inside. But to do the derivative of the inside required another chain rule. Right? So we had one chain rule nested inside of the other.
So it's the chain rule of g of h of x and the chain rule of h of k of x.
Yeah. So we did one chain rule on g of h of k of x. And then to do the inner piece, to do the derivative of h of k of x required another chain rule. Yeah. So you had like two chains linked together. That's kind of why they call it the chain rule, because you can just keep linking them together. But here's the nice part. Like, this looks awful, right? But to actually do this, now to fill things in, is really pretty easy. So just using my basic trig derivative rules, which again, if you haven't started memorizing yet, you'd want to get on that. Make yourself some flashcards or a Quizlet or whatever you like to do. Those trig ones you gotta have memorized. So g prime is cosine, and then h of k of x would be cosine of tangent. And then h prime is negative sine, and then k of x is tan x. Oops, that's a little big. And then k prime of x is now, can I simplify this anymore?
I'm going to say
No, you can't, because you don't have multiplication of trig functions. You have composition of trig functions. So like cosine of cosine is not cosine squared, right? Because it's not cosine times cosine. Yeah, so it's not the same thing, right? So you got to be careful about that. Does that feel okay, what we did there? A, B, C, D, E, F, G, H. Thanks, man. Okay. What do you guys see here? Yeah, two chains, right? So f of x is e to the x. G of x is secant of x. And k of x is 3x. So what we have is y is equal to f of g of k of, and I'm going to change back to theta since that was the variable in my problem. Everybody cool? Well, this is convenient because this is the same problem that we just did. Which is the lovely part about thinking about this symbolically first, because you're going to see that, like, oh, any problem that's just two chains, it's the same derivative. The derivative is the exact same form every time. It's just a question of, like, getting the derivatives, right? It's exactly what we wrote before, except I had x's instead of thetas. But, like, whoop-de-doo! All right. So derivative of x is e to the x. Derivative of g of x is, yeah, good job, secant x times tangent x. And derivative of k is 3. Okay. So I'm going to have e to the secant 3 theta, and then secant 3 theta tangent 3 theta times 3.
You would actually write it.
Well, I'll talk about the test format a little bit later, but, like, 2 chains would not be enough.
Like 5.
And
a quotient.
So, like,
5 chains.
so you'll have, like, I think I've already got this first test made up, but there'll be, like, a set of questions that can be done with no special rules. You don't have to use the product, quotient, or chain. There'll be a set of problems that you can use that can be done using just one of them. A set of problems that could be done using 2 of them. And then, like, a set of problems that could be done using 3 of them. Now, when I say can be, yeah, when I say, then there'll be fewer problems in each section because obviously they get more time consuming as you go. And when I say can be, like, certainly you could use more than that and still get the correct answer, but there might be, like, algebra stuff that you could use before that to simplify down to, like, oh yeah, I could get rid of doing a quotient and chain here by just doing one chain with, like, a negative exponent like we did before or something like that. Teagues.
When are you thinking the date on the test is going to be?
Not this week. So that I know that much. Okay. Let's do H. What's next? I. Yes, sir.
So when you have an e to the x as one of your derivatives for, like, a chain rule, then everything that's in that composition goes into the exponent of the e to the x. Okay.
Yeah, that's what the composition looks like, right? Because we're plugging it into where the variable is, and the variable's in the exponent. So all the stuff just goes into the exponent. That's what you're asking?
Yeah.
Okay. Here's a fun one. Right? Because how do you write this as compositions?
Like I'm like trying here.
Yeah, it's not at all obvious. This is one where I would probably just attack this without doing that symbolically, because coming up with a way to write the composition feels really difficult because I have these x's in each layer. Yeah, so I would be thinking about this. with exponents. So this is my first inner, right? So there's the derivative of the outside. Now when I take the derivative of the stuff in yellow, I'm going to get 1 plus, and then to do the derivative of this piece now is going to require another chain rule.
Explain what you just did with that last equation.
Yep. So I took the derivative of the stuff in yellow until I got to the green piece, which requires a chain rule. Right? So the derivative of x was 1. But when I get to the green piece, that required a chain rule. So I did the derivative of the outside, and now I have to do the derivative of the inside. I get that yucky looking thing. Okay. So let's try to do that. This one is quite tough. Let's be clear. This is quite bad, or quite difficult. All right. So I looked at the whole thing. Right here is the derivative of the first outside. Okay. So now I'm going to be doing the derivative of the inside. So when I get to the x, that's the 1. Good with that. When I get to the plus, the quantity x plus x to the 1/2 all to the 1/2, that requires a chain rule. So that's the derivative of the outside for this piece. Right? And then this would be the derivative of its inside. I think the hardest piece is like keeping all the parentheses in the right places on a problem like this. Quite difficult to do that. Mostly because where the x's are located, it's not an obvious way to write the composition here. If these were like 1s instead, okay, we can do that. That's not so bad, but because there's x's on every layer, I looked at this and I'm like, I don't know how to write this as a composition. I sat there and I looked at it for quite some time and I'm like, I can't come up with a good way to doing this. Tegan.
Could you have written it with exponents like x to the 1/2 plus x to the quarter plus x to the 8th?
No, because exponents don't distribute.
Okay.
Right? So you can't like distribute those exponents through.
Okay, yeah.
Right? Yeah. Right. If you could do that, then it's simple.
Yeah.
But yeah, exponents don't distribute, so that's a toughie right there. All right. I got one more real nasty boy for you here. You're going to love this. So when you look at this, what do we see?
Chain rules
over a chain rule.
I see 3 chains,
Yeah.
a quotient, and a product.
Yes. That's all.
This is a big beefy boy right here. All right. So start by thinking about it just as a product, right? Or a quotient, excuse me. Everybody's okay here? But g of x, we're going to think about as j of x times k of x. And h of x, we're going to think about as jk L of m of x, where L of x is x to the 7th, and m of x is 8 minus x. So now my derivative becomes h of x times j of x times k prime of x plus k of x times j prime of x minus g of x times L prime of m of x times m prime of x all over k of x squared. But here's the problem. K of x and j of x are both required chain rules to do them. I'm running out of letters in my alphabet.
Will it ever be in this class where we're gonna like have to start hitting Greek letters?
Oh, I don't know. I forget now what
I think that'll be our extra credit.
K, okay. Oh. H, did I do this wrong? What is H? Okay, H is the denominator, okay. So K was that guy, okay.
Wait, so is that down at the bottom, k squared of x, wouldn't that be like L? But like where did k of x from?
Okay. Did I copy the K in the wrong spot?
I really don't
Down
know.
here?
I'm
Oh,
gonna
yeah.
be completely honest.
Yeah, that was supposed to be H, sorry.
And then, but it doesn't actually become L of m of x right now?
No, because I don't need to do the derivative of it. So I don't need to mess with the composition. H of x can be H of x unless I'm doing the derivative of it. I don't want to write it in a more complicated fashion.
Yeah, okay.
Only if I need the
smart.
derivative to do it.
For clarity's sake, do you mind doing P instead of O? That it's like a 0 in my brain.
Yeah, sure.
Wow.
No problem.
Wait, I'm confused with what you're doing here.
Uh,
After like the big one.
So I now need to use a chain rule to do these guys. So that's what I'm doing, is I'm just writing those guys in a way that I can do the chain rule on. Oh, I shouldn't write K prime, I should just write K. So J is going to be MNOP. So Q of R. So Q of X would be, this is just X squared, and that was X plus 2. Okay. Woo! Now here's the good part. From here it's easy, right? Because the derivative of n of x, 100x to the 99th. Derivative of p of x, 3 minus 20x to the 4th. The derivative of q of x, 2x. The derivative of r of x, 1. Go back up here. The derivative of L of x is 7x to the 6th. And the derivative of m of x is negative 1. So now we just need to plug things back in. And we are going to be dunzos. So h of x was x, 8 minus x to the 7th. J of x was x plus 2 squared. N prime was 100 something to the 99th. The p of x that's plugging into that is 3x minus 4x to the 5th. And then p prime of x is 3 minus 20x to the 4th plus. And then k of x was 3 minus 4x to the, 3x minus 4x to the 5th to the 100th. And then q prime was 2, and then x plus 2 times 1. That was q prime of r of x times r of x, or r prime of x. And that closes that, minus g of x, which was x plus 2 squared times 3x minus 4x to the 5th to the 100th. And then L of x is 7, and then x to the 6th, which was 8 minus x times negative 1. And then all of that over 8 minus x to the 14th. That would be 7 squared. I just wrote it as the 14th.
Can you zoom in to that last?
No, this is like a nightmare. Like even when you're like very good and confident, like this is a nightmare problem.
That's not like a test question.
If you put this on
Ain't
a
no
test,
way
I would
that-
respectfully
ain't no
put
way
a
the
heart
College Board
and then
is,
just like leave it.
This is just hideously like a lot of grind, right? Like this is just like long and unnecessary. But here's the thing: if you can do this, what's your confidence feel like? Like you can do anything at this point, right? Like it's not gonna get worse than this.
I mean, we could have had 2 quotient rules.
Well, yeah, I mean, like, here's the thing, Blake. If you have 2 quotient rules in the same problem, you can algebraically just turn into 1 quotient rule
Okay,
by
that's true.
by like simplifying the complex fraction. You'll end up with possibly more product rules after that. But I would rather probably do that
Do the product rule.
than do 2 quotients in there.
Yeah.
So like getting much worse than this, I don't know that would be possible other than putting like a product into the denominator also, which is just like mean. Well, an extra variable.
Oh, but then it would just be a constant.
Yeah.
Yeah.
So unless you're all of a sudden want to jump to like Calc 3 in college where you do multivariate calculus, then we don't have to worry about it.
Yeah. I think I'm gonna stick to this.
Let's say
Perhaps.
Yeah.
Do you think they all do that now? Oh.
what do you mean? Do you think? Yeah.
Okay.
No,
All right. So last thing,
Wait, can you go back to the denominator of that?
it was 8 minus x to the 14th. What's up?
Do you mind following that up?
Yeah. I mean, you could do some simplifying. I see some right away if you want to talk about it. So, like, here's what I notice. That first term has a factor of 8 minus x to the 7th. The last term has a factor of 8 minus x to the 6th. So I could do that right away. That's nice. Anything after that is just going to be some simplifying, and I'm not dealing with much of that. I mean, you could factor some stuff out, but it's I don't think it's ever going to get very nice looking. Teagues.
Did you have to do the chain rule to the denominator at the beginning?
The h of x, I only did the chain rule on h of x when I took the derivative of it, which happened right here.
Okay.
That was the only time I had to do anything with h of x.
Okay.
I mean, there's a lot, right? There's a lot. Would it ever get worse than that? God, no. No.
So we can only really have one problem.
Yeah.
I don't think that I can really do much more than that.
No, of course not.
Should
Yeah.
the option be like that?
Like, what do you do with one of them? Trust me, I'll give them an answer.
Okay. So you guys remember this derivative rule from we cooked this up. I think even at the end of chapter 2 we noticed this was going on. We're now ready to prove this because we needed the chain rule to do that. And here is the trick. I'm going to rewrite a as e to the natural log of a. Notice that's still a, right? And then that's all to the x. So now that's the same thing as a to the x. And I know the exponent of an exponent multiplies. So I know that. So that's a chain rule problem now. the outer function is e to the x, so the derivative is just e to the natural log of a times x times the derivative of the inner. What's the derivative of natural log of a times x? Natural log of a times 1, right? Natural log a is a constant, so. And then note this piece is the same as a to the x. So we're all done. That was our proof. Well, that's not so bad, Mr. Kulik. And this is, now you can really see that the derivative of e to the x is just e to y, it's just e to the x. Right? Oh, okay, sure. That's why it just, yeah, sure. All right, so this is page 205. Most of these aren't bad.
Most.
Well, like the 1 through 45 odds, like most of those are like a single chain rule problems that should be pretty quick.
Okay.
So 53.
Yes. Yeah, just 51 and 53 basically, right? Probably could have written it that way, would have been less symbols. Here. Do that, that's less symbols, right?
Wait, no more 55? 59.
There was never a 55. Of course, yeah. Yes, of course. Luke, you had questions?
So for the AP practice problems, 18, I cannot understand the logic behind the answer.
Okay, let's take a quick look here.
Oh, I needed my dad.
Oops.
Dang. I don't know how to do that. That's
My dad had to dust off the 30-year-old calculus.
Hold on a second. Let me pull it up here. You said 18?
18, yeah.
That was the worst one, everybody agreed?
That was the one I understood.
The one we understood the least, okay.
I mean, it was like all like conceptual stuff.
Yeah, those are my favorite ones.
I hate those.
Oh, yeah, no, this one I know.
Like I was like,
All right, let's take a look. Was this the odd and even one? Like the odd function, even function?
Yeah.
Yeah.
I don't really understand. What is this? Is that O? Like the letter O?
That's just like, you could think about that as like f prime of a, right? It's just
Okay.
x naught, so it's like
So
a
it's
zero
just a
subscript.
constant of X then.
Yes.
Okay.
Yeah. It's just like f prime evaluated at some specific value.
Yeah.
You know, supposing that exists. So here's the way I would think about it, is I would think about what I know about polynomial odd functions and polynomial even functions is the easiest way to kind of conceptualize this. So if I have some p of x is a polynomial, if p of x is odd, the degree of each term in p of x is also odd. So for example, we'd have like, x to the fifth plus x to the third plus x to the first. And the same thing about evens. So for example, like x to the fourth plus x squared plus 1 is even. So if I take my odd function, call this odd, I would get like 5x to the fourth plus 3x squared plus 1. What do you notice here? It's even, right? Another example, you remember the graphs for sine and cosine function? Sine is odd, cosine was even. So the derivative of my odd function is an even. At this point, I'm pretty convinced that the derivative of an odd function is just going to give me an even one back. Cool with that? So my definition of an even function was this. So for my problem, if f of x is odd, f prime of x should be even, which says then that f prime of x naught, negative x naught, should just be f of x naught, which is what I'd want to pick here, response A. That's how we're supposed to do that, is you had to remember stuff from first semester of Trig and Pre-Calc when we talked about odd and even functions. And then really remember, like, what's an example of an odd function that I can take the derivative and kind of just see what happens? That's what you needed to just see that, oh, okay, derivative of an odd function is going to be even. And then I know what the definition of an even function means, that f of negative x has to equal f of x. So there we go. It was hopefully that would have been the thought process. Now, I kind of explained how I got to that thought process a little bit, but ideally that would have been instantaneous almost. Like, okay, odd function looks like this. What's an example of that? Okay, take the derivative. I get an even. Okay. F of negative x equals f of x. That should be it. If it worked once, it should work every time, or else they wouldn't be asking me a question like this, right? Like, like that's the way I would be thinking about it, though. Is that?
Yeah.
Jack?
Could you explain number 19?
Sure.
I'm not sure.
Okay. Let's do this. All right. So y prime is going to be 1/2 times the exponent, x to the exponent minus 1. And then I'm going to think about this piece as minus 3x to the negative 5th. So if I simplify that out, I got 2/5 x to the negative 1/5 plus 15 x to the negative 6. This one. Does that make sense?
Yeah, I subtracted -5 minus 1 to -4.
Oh, you gotcha.
Yeah.
And I guess on this one, even like the smartest way of going about it would have just been like looking at the exponents initially and go, okay, I need to have 2 negative exponents in there. So like already this one is gone and this one is gone. And if you looked and go, okay, well, that needs to go to a -6, so that's gone and that's gone. And you can get to the right answer without actually having to do any real derivative at all. You're just kind of like eliminating the impossibilities.
Yeah.
But yeah, that's the gist of it. You just made a goofo. How's everything else going for everybody? Is this chapter feeling a little easier?
It's better, yeah. It's way easier.
Yeah, I think the worst conceptual stuff is really kind of behind us. And then from here on out, it'll be, I mean, there's still conceptual things, but it's a little bit more, like we've laid the most difficult foundational stuff. And I think that'll continue to like pay dividends as we go further. Yeah, and again, like with the homework problems, I'm trying to assign stuff where like there's review from algebra pieces built into it. Like I'm trying to pick out a lot of the problems, especially the later ones that are like you need ideas from algebra, pre-calc, or trig, or whatever to kind of like do the problem, just to get used to connecting back to that material. A lot of solving system stuff has come up here in chapter 3.
I have no idea. I didn't know that.
Yes.